Hello, my name is Abdulrahman. I am a PhD student at the University of Colorado Boulder, and I am presenting our paper, A Global Measurement of Routing Loops on the Internet. First, to agree on the terminology and to provide a quick refresher, when we say routing loops, we refer to the situation where packets sent from a source never reach their intended destination, because the packets are being forwarded between a set of routers until their TTLs expire. And as a result, the source may receive an ICMP time-exceeded message. Also in this talk, I use the terms routing loops and forwarding loops interchangeably. In terms of the persistence of routing loops, there are two main types. First, the transient ones. They typically happen during routing protocols convergence and resolve automatically. The second type is the persistent routing loops, which are typically caused by inconsistency, misconfiguration, or errors in routing protocol implementations. And these persist over a long period of time, usually until a manual fix is introduced. In our study and in this talk, we are focused on the persistent routing loops on the Internet. As a motivation, let's first look at why these loops matter. So it has been demonstrated in the literature, in fact, recently, that routing loops can be leveraged to carry out attacks that disrupt the Internet. Attackers, for example, could flood links that are shared between looping and non-looping destinations by leveraging the fact that the packets stay longer in the loop. Also, middle boxes that happen to be in the path of routing loops have been exploited to launch denial of service attacks, both in TCP and also in UDP, specifically with DNS traffic. So we find these to be compelling reasons to further investigate the state of persistent routing loops on the Internet. Now I will be talking about how we detect these loops. Normally, routing loops can be detected from traceroute data. So this presents the following question. If we want to detect all loops on the Internet, do we need to traceroute the entire Internet or just a few IPs per BGP routed subnet? A follow-up question would be, should we traceroute the entire Internet using the entire TTL space of 255 values? Well, this is exhaustive and impractical because we will need to send roughly 2 to the power of 32 times 255 probes in order to complete an Internet scan to detect routing loops. So we have to pick between either limiting the TTLs or limiting the number of IPs we traceroute. And just as a reference, existing efforts that aimed at mapping the Internet topology traceroute only a few IPs per subnet, but use more TTL values. So if we follow their methodology, although it is meant for mapping the Internet topology and not for finding routing loops, if we follow their methodology, meaning that we scan a few IPs per subnet, are we going to be able to detect all routing loops on the Internet? A quick answer to this is no, and we will see why in the coming slides. So what should we do? More IPs and less TTLs, or vice versa, or what? The final point here that should lead us to the answer, recall that if we send a packet with a TTL of 255 and yet receive an ICMP time-exceeded message, this means that either the destination of that packet is 255 hops away from us, which is quite unlikely in today's Internet, or that the packet has been forwarded many times inside a routing loop until its TTL expired. So as insight from all of this, to find routing loops, we can scan the entire Internet, yet we don't need all TTL values. It is sufficient, in fact, to use a few high ones. Before embarking on any scanning activity, we ask a few questions. that would help inform our scanning methodology and help us parameterize the tool we use. More details on this in the paper. So now, how do we conduct our scanning? On a high level, we use YARP, a network topology discovery tool, to scan the entire IPv4 space. We scan the internet once per TTL value in the range of 246 to 255. For example, we start by scanning the internet for TTL of 246, then scan the internet again for TTL of 247, and so on until we complete all 10 TTL values. This helps us avoid routers' ICMP rate limits because each destination is probed once per TTL value instead of 10 times at once. And once the scans for the TTL range are complete, we repeat the process again, meaning that we run back-to-back scans for the 10 TTLs. In other words, we run the first scan. Once it's done, we run the second scan. And then we calculate the set intersection between the loops we find in each of the two scans. And the way we find routing loops is by reconstructing trace routes from the scans data for each TTL value. Then we examine these trace routes to look for repeating router IPs in accordance with a specific heuristic that we detail in the paper. And as a result from our scanning, our data set shows that 24 million destinations on the internet suffer from persistent routing loops. That's about 0.6% of the entire IPv4 space. Compared to the looping destinations found in other public distributed datasets combined, namely RIPE Atlas and KDA-ARC, we find 21 times more looping destinations in our dataset. Note that these methods don't trace route the entire internet at once, suggesting that scanning the entire internet correlates with finding more looping destinations. Now let's look at why these loops happen in the first place. One of the root causes of these loops is the common misconfiguration of not setting up a null route for unused IP addresses, and instead forwarding traffic destined for them to an upstream provider or another router at the same AS, creating the looping behavior. The second cause of these loops is the misconfiguration of middle boxes, in this case, specifically NAT devices. This type of routing loops happens when the destination IPs being probed are meant to be used for NAT translation. Yet an active translation does not exist at the time of the probe. So packets are forwarded upstream. Another type of routing loops that are caused by misconfigured middle boxes happen when firewalls reroute TCP packets that are not part of an existing TCP flow, nor initiate a new one, instead of just dropping them. For example, when we send SYN packets to this IP with the following TTL values, nothing happens. But when we send the same packets, but with an ACK flag instead, a routing loop is observed. The third cause we find is a misconfiguration, potentially on the destinations themselves. As we can see, this trace route, the destination IP itself responds with ICMP time exceeded messages. We can't tell for certain whether there's a routing loop or not, but we ran follow-up trace routes from TTL 1 to 255 and noticed that the round-trip time of the ICMP messages we receive follows a monotonic upward trend, indicating that our probes spend more time in the network as the TTL value increases, which can be indicative of a looping behavior. Now we try to validate our results. First, we ask, are these really persistent routing loops? Or is it the case that the number we find is an artifact of our methodology or the tool we use? Also, are these loops only visible from our vantage point? So we obtained a second vantage point in a different AS, in a different organization, and we simultaneously ran internet-wide scans with our original scan using the same scanning methodology and the same tool. We find over 23 million destinations looping from the perspective of both vantage points. We also compare our results with previous scanning activity we conducted 6 months before the study using the same tool, the same methodology, and we find a high degree of overlap with our current results. Now, looking back at our methodology, we analyze our results and ask a few questions that we think can help inform the scanning decisions of fellow researchers. Basically, did we really have to scan the entire internet to find routing loops? What if we just scan the .1 address for each /24 subnet? If we do that, we will be missing over 73% of the loop containing /24 subnets. So what if we sampled /24 subnets? To answer this question, let's look at the number of looping IPs per loop containing subnet. Only around 10% of the subnets experience routing loops on every IP in the subnet. And around 35% of subnets have at most 10 looping IPs. So sampling /24 subnets won't help us here. So what if we want to optimize the volume of future scans to minimize the number of probes we send in order to discover all loop containing subnets, just these /24 subnets? What last octets reveal the most subnets? We analyze our data set and find that these 4 last octets reveal around 50% of subnets. The CDF shows the number of ranked IPs needed to reveal the most loop-containing subnets. And we can see that to reveal around 92% of loop-containing subnets, one needs to scan the top 50 IPs in terms of their revealing rank. We think this plot, along with the previous one, are 2 good examples of why we need to scan the entire internet to detect all routing loops. Finally, we examine the significance of the routing loops we find. So routing loops have been used to carry out attacks on the internet. So what's really new here? To provide some context, 2 years ago, a new TCP reflected amplification attack was discovered, which in part leverages censoring middle boxes inside routing loops. And the attack happens when an attacker sends a packet with a forged source IP and a sensitive keyword to a looping destination where a censoring middle box happens to be along the path and inside that routing loop. This packet triggers a response from the censoring middle box to the victim each time the packet passes that middle box in the loop. So this has already been known. What's not known was how many looping destinations on the internet can be used in this attack, and what routing loop types provide the most amplification. So we ran an experiment where we send a single pushback packet with a GET request containing a sensitive keyword to the looping IPs in our data set. We were able to elicit a huge amplification factor up to 1.4 million X. And we can see from this IP rank plot that over 6,000 IPs have an amplification factor greater than or equals to 100. And these IPs are in 119 different ASs and in 13 different countries, making them an attractive target for an attacker given the diversity of these networks and bandwidths. And with this, I conclude. Thank you very much.